The next idea we are going to study is Kirchhoff's laws for the circuits containing resistors and cells. So the first law we study is law of current or law of junction. Consider a junction in the circuit or a node in the circuit which has many wires connected to that particular point. So this is a point from which a lot of wires are going out, and then here are the currents that the wires are carrying. So there are some wires which are carrying the currents towards the junction, while there are other wires which are carrying the currents away from the junction. According to charge conservation, whatever charge is being delivered to the junction, that charge cannot accumulate there, it cannot get destroyed, it cannot be created. Therefore, whatever charge goes towards the node or the junction, the same amount of charge must come out also. Hence, this dictates that the total current which is going in or towards the junction must be exactly equal to the currents which are coming out. So for this particular junction, we can now write the total currents which are coming in or going towards the junction. They are I1 plus I2 plus I4, and that total current must be equal to the currents leaving the junction, which is equal to, in our case, I3 plus I5. So this is what is called the Kirchhoff's law of current or law of junction. The second law is the law of voltages or law of a loop. Imagine here's a circuit given to us like that. There are some cells in this, there are some resistors like that. The cell, those V1, V2, V3, they are the battery voltages, the cell voltages, or the cell potential difference. And then it is also given to us that in this particular part of the circuit, of course I am not showing you the complete circuit. The complete circuit may be quite big, quite complicated. We are looking at only a particular part of the circuit, and in this particular part of the circuit there is it is given to us that there is a current I which comes from this branch like that, and there is a current I1 which leaves from this branch like this. We are interested in a general analysis of this circuit now. Now the first thing we have to do is spot a loop. The loop doesn't have to be circular in nature. All you need is a path which is closed around it. So that path can have any shape, any size, it can have anything along the path, yet the only requirement is that the path has to be a closed path. For example, in this diagram, you realize that this quadrilateral looking thing, that is a closed path. So we can now apply the law of loops here. If I start from this point and if I start calculating the potential differences, so I'll go here, there is a potential difference, and if I start calculating the potential differences along the closed loop, and if I come back to the same point again, what would be the net potential difference? If I add all of them along the closed loop, obviously 0, because we know if I start from this point and this point has a particular potential, and if I come back to the same point, whatever way we want, whatever sense we have, it doesn't matter. If I come back to the same point, then the total potential difference calculated for this patch, this, and then coming back here, that total potential difference has to be 0, because electric field or electric force is a conservative force. As a result, the total work done over a closed path has to be 0. In other words, this statement that if I start from this point and if I start counting or measuring potential differences here, and if I come back to the same point again, the sum of those potential differences is 0. This is nothing but the statement of conservation of energy. Therefore, using that statement, that sum of the potential differences over a loop has to be 0. This is nothing but energy conservation, and we are going to apply to the loop this statement. Now, One of the most important things that we have to understand in application of Kirchhoff's law, especially the second law, voltage law, according to voltage law, we have to choose a sign convention. That sign convention is this: if you are going over a branch, over a resistor, if you are going over a resistor in the same direction as current, then the voltage or the potential difference across the resistor is negative. I'll repeat. If we are going over a resistor in the same direction as current, then current through that resistor, then the potential difference across that resistor is taken as negative. On the other hand, if you are going over a cell, then the potential difference of the cell is taken as positive if we are going towards a positive terminal over a cell, and the potential difference is taken as negative if we are going towards a negative terminal. Let me put this into action like this. So we have a loop. Then the first thing we have to understand is choose the sense of the loop. Now you may choose the sense of the loop any way you want, and we have only two options anyway. Either you can go clockwise or you can go anti-clockwise. So you can choose any sense as you want, but the point is that you have to choose a sense. So here in my diagram, I am going to choose anti-clockwise sense to go over the loop, and I show it like this. I also choose a starting point. That also is completely our choice. So I'm going to start at this particular point here, and then I'm going to go over the loop like that in that sense, and then of course I'll say that the total sum of the potential differences is 0. But the next job, having done that sense and having chosen the starting point, the next job is to assume currents, and I'm using the word assume in a very deliberate manner. So what do I mean by that? So suppose this is given to us that the current I is entering this circuit, then I'm going to assume that this current splits into two parts. Here's a current I2, and obviously if this current is I2, which is again my assumption, then by Kirchhoff's current law, the junction law, if current I is coming here and I2 goes like that, then the remaining current must be I minus I2. So I will write it here. Fine. Now that I2 goes there, and then I2, one part of I2 is I1, which goes away like that. So again I am going to say that there is a current here which goes like this, and that current is I2 minus I1. So current I2 comes here, I1 goes like that, I2 minus I1 goes like that. Again I am using the junction rule or Kirchhoff's current law here for this junction. So now we are having I2 minus I1 which comes here, and we are having some picture here. So let's say that I2 minus I1 comes here. Some current I3 now goes away like this. Now given that I3 goes away like that, you can say the current I2 minus I1 comes down like this, and out of that there is a current which comes like this. So we now say that I2 minus I1 comes here, I3 goes there. So the current which goes in the remaining current which goes here, that must be equal to I2 minus I1 minus I3. And thus now we have got current in every single path of the loop. We've got here, here, here and here. So coming back to that word assumption, we just blindly assume that the currents are like that. Are they really like that? We don't know. In fact, what if I'm wrong? What if the current I2 is not really like this and the current I2 is going the other way? Then in that case, after all the analysis here, I will find that current I2 is coming out to be negative. If I find that current I2 is negative, I will conclude that my assumption of this direction is wrong, and the current actually flows in this direction. So that is a nice thing about Kirchhoff's laws. It doesn't matter what assumption you make, as long as you follow the correct sign conventions, you will always get correct answer. Kirchhoff's laws will always rectify your assumptions. So now we will start applying the Kirchhoff's voltage law, and it goes like this. As I said, I'm starting at this point, I'm going in the anti-clockwise sense, so I will go like this. So the first thing I encounter is the cell, this cell, and as we see now, I'm going from positive to negative terminal here. Hence the first term, since I'm going towards the negative, from positive to negative, I have to take the negative sign. Hence the first term I have to write is minus V2. Then I realize that I'm going in over a resistor R3, but I'm going in the direction opposite to the current. See, the current in this branch is like that, but I'm going over the loop like this. Therefore, I'm going over R3 in the direction opposite to current, and hence now I should take the voltage or the potential difference across R3 as positive, because I'm going in the direction opposite to current, and that using Ohm's law will be equal to this much. Then I will go up. Once again I am going over a resistor, but in the direction opposite to the current. Hence the potential difference across R2 is also positive. So I'll again add another term there, which is I2 minus I1 multiplied by R2. Then I come to this branch, and when I come to this branch, I'm going over a cell, but I'm going from negative to positive terminal. Hence the potential difference or the voltage across the cell is considered positive. That will be plus V1. Then I go over a resistor R1, but again I am going in the direction opposite to the current, and therefore I have to now take that as plus I2 R1. And finally, for the last part of the closed loop, I am going over a cell here. There is no resistance, please understand that. And since there is no resistance, the only element here remaining is the cell, and I am going from a positive terminal to a negative terminal. Hence the voltage across the cell is negative V3. So I'll do that. I'll add minus V3. But then I realize now I have come back to the starting point here. Hence the total sum is 0. So this is how we apply Kirchhoff's voltages law and Kirchhoff's current law together. Just to summarize, Kirchhoff's current law, which is also known as KCL, Kirchhoff's current law, is a statement of conservation of charge, whereas Kirchhoff's voltage law, which in short form is known as KVL, Kirchhoff's voltage law, that is a statement of energy conservation. Combining these two, we are able to analyze all kinds of circuits that that we may encounter. Just remember though that sign convention is very, very important, and it has to be strictly followed. Just to repeat the sign convention, whenever we go over a resistor, if we are going in the direction of current, then the voltage or the potential difference across that resistor is considered negative. When we go over a cell from negative terminal to positive terminal, then the potential difference of the cell or the voltage across the cell is taken as positive, and vice versa. So having understood these concepts, now we will begin a very important discussion called EMF of a cell, or the electromotive force of a cell or a battery. So let us talk about a cell or a battery. Now all of us use these things in our daily life, so we are very well aware what a cell is, what a battery is. We know there are different kinds of cells. Usually they are denoted by AA, AAA, those kind of notations. We know that depending on your application, maybe you want those cells to be in an electronic device, like for example the remote control of your television, or maybe you want them in some kind of a toy, and then according to your requirement you go to the market and you ask for that type of a cell, and that is what we are holding. Usually they are called a dry cell. So when I hold a dry cell in my hand like that, then I am having a situation like this. Inside, so this blue box is what I'm holding in my hand when I hold that dry cell in my hand. Inside this dry cell there are these two terminals like that, and there is some kind of a chemical which is stuffed in this box, in this cell. Because of the chemical reaction there, because of the nature of the chemicals involved and the chemical reactions involved, there is a separation of positive and negative charges that starts. Now this separation of positive and negative charge is actually arising out of the chemical nature, the chemical reactions that are taking place inside this cell. But from physics perspective, you could also say that forget for the time being what chemistry is happening there, forget for the time being whatever chemical reactions that are happening there. We will say that from physics perspective, there is some kind of a force which the cell exerts on the charges. In other words, in this space, suppose we are now inside the cell, and effectively from physics perspective, there is some kind of a force which is acting on positive charges, and that force is pushing the positive charges to this terminal. Now who's exerting this force? Well, this force is obviously exerted by the cell, the material of the cell you could say, the arrangement of the cell you could say, and that force is denoted by FB, in other words force by the battery. Please understand, this force by the battery is strictly a non-electrostatic force. So we are saying that there is a force which acts on these charges, but the force is really arising out of the chemistry, arising out of the chemical reaction, chemical interaction of the material here. Hence, we realize that this force is strictly a non-electrostatic kind of force. It is in fact a battery force, a sort of a chemical force, and hence we denote it by letter FB. Due to this force, positive charges, they start getting separated. In other words, you could also say due to the force, positive charges they go from this terminal to that terminal. As a result, positive charges start depositing on this part. But if I claim that, or if I say that there is a battery force which is pushing the positive charges in this manner, then effectively what we are having here is deposit of negative charges. So now on this terminal you start to have a deposit of negative charges. You can see as the battery force FB pushes more and more positive charges on this side or more and more negative charges on this side, within the cell there is now an internal electric field. See, this electric field was non-existent in the beginning. Battery forces started operating those, started separating the charges like that. Because of the separation of the charges now, internal, within the cell, there is now an electric field which of course goes from a positive to negative terminal. So now we realize there is an electric field like this, and that electric field is causing an electric force or electrostatic force. So now whatever charge is here, we realize this charge in this space in general is experiencing two forces. The first force is the battery force. The other force is this electrostatic or electric force, which is simply coming from the attraction due to the negative charges here, or it is coming from the repulsion of these positive charges. But as these positive charges start to increase, in other words, as these negative charges start to increase, this force or the electric field inside, that also starts to increase. So you can imagine now there's an electric field in this region, which I will denote by this arrow, and that electric field I will denote by letter EE. Again, that is electric field. So as the charges build up here, electric field increases. That means this electric force increases, and eventually there will come a time that the battery force and electric force will exactly equilibrate with each other. In other words, they will become exactly same. Now the battery force is constant because it is arising solely out of the chemical reaction, the chemical interaction in the battery. Hence, battery force is constant, but this force keeps on increasing. So there comes a point where the battery force and this force, they will become equal, and once they become equal, that means the net force on this charge will now become zero, and at that point the charge separation will stop. When the charge separation stops, we say now the cell is in equilibrium, and when that equilibrium is achieved, now there is a permanent deposit of positive charges, there is a permanent deposit of negative charges. Don't forget, the net force acting on any charge in this region is now zero, so these positive charges cannot go there, and the same way these negative charges cannot come here, and therefore there is a permanent deposit of positive and negative charges on these terminals. Given that fact, now there is a permanent deposit of positive and negative charges. In other words, what we have created in the cell is now a potential difference between this one and this terminal, and this is what you call as the positive terminal of the cell, and that is what you call the negative terminal of the cell. So when you hold the cell in your hand like that, and one is positive and the other is negative, what you are holding in your hand is this situation. So I am interested in finding what is the work done by the cell in moving a charge Q, of course a positive charge Q, from a negative terminal to a positive terminal. So how much is that? Well, of course it is the work done by the battery force, and that is nothing but FB multiplied by D, where D is the separation between these two terminals. So it is FBD. Oh, we know in equilibrium, whenever that equilibrium is achieved, FB is exactly same as the electric force. So I can replace that FB by FE only for the sake of magnitude. So in magnitude, the battery force is same as electric force, so I will replace that. So I get WB, the work done by the battery or the cell, equal to FE multiplied by D, but the electric force in magnitude will be given as Q times electric field. So that will give you Q times electric field multiplied by D. But we know the potential difference here can also be written as, or rather electric field here in equilibrium, of course, will be written as delta V divided by D. That is coming from the electrostatics. So given that electric field here, when it reaches equilibrium, of course, that electric field is nothing but the potential difference divided by the separation. So that gives me that separation multiplied by electric field is nothing but the potential difference across the terminals. So here I am using the idea that delta V is equal to electric field by D. That electric field is delta V by D. So using this relation now, I go to this point, and therefore I find that the work done by the battery is Q delta V, where delta V is nothing but the potential difference created here due to the charge separation. But then we say what will be the work done per unit charge. So that work done by the battery per unit charge, meaning WB by Q, is nothing but delta V. Now this left hand side quantity is defined as the EMF of a cell. So we define this quantity as EMF, and it is denoted by letter big E. So in other words, what is EMF of a cell? EMF of a cell is the work done by the cell in moving a unit positive charge from negative terminal to positive terminal. Of course, if I put that Q, or that is nothing but the work done per unit charge. It is also the potential difference though. So it is a potential difference across the terminals. But don't forget, we haven't used this cell, or we aren't connecting this cell in any circuit. Hence, the second meaning of EMF of the cell is the potential difference across the terminals when the cell or the battery is not connected in a circuit. See, because in this thing, it is not at all connected in a circuit, and yet I am getting that delta V. So what is the meaning of delta V here? When it is not connected in the circuit. In other words, it is also the potential difference across the cell terminals when the cell draws zero current. When we say cell draws zero current, that means the current through the cell is now zero because it is not connected in a circuit. So these three statements, they are all equivalent to each other. Work done by the cell in moving unit charge, and hence we realize the total work done So the total work done when the battery sends a charge Q, or when it goes from negative to positive terminal, that is nothing but QE, which is the EMF, or Q delta V. Again, delta V is the potential difference across the terminals when the cell doesn't have any current through it. So given this idea that work done by the cell is this EMF, we realize EMF is slightly a misnomer. I mean, we are calling it an electromotive force. It's not a force, it's really work done. It's not even a work done really, it is work done per unit charge, and it turns out to be delta V. In other words, the SI unit of EMF is simply volts. Now suppose this cell that I have shown you there, that cell actually doesn't have any resistance inside. But in reality, you will find that this flow of charge, which is going from negative terminal to positive terminal, this flow of charge from this to this place, that flow will certainly encounter resistance as it goes through the material. So that resistance encountered by this charge as it goes through this material, that is called the internal resistance of the cell. And thus we now define two kinds of cell. A cell whose internal resistance is zero is called an ideal cell. So that internal resistance 0 is usually, that internal resistance is denoted by small r, because you can imagine you don't want the internal resistance anyway to be very high. Such a cell is called ideal cell, where internal resistance, that is small r, is 0. On the other hand, there may be cells whose EMF is very, very precisely known. So a cell whose EMF is known precisely, that is called a standard cell. So if you go to the market, and as you know, the most common type of the batteries we use are 1.2 volts cells, which you also call AA batteries or AA cells. And then we know that AA batteries or AA cells have that voltage 1.2 volts. So a good question we could wonder about is that 1.2 volts is exactly what? Well, since you get that and it is not being used, that 1.2 volts is the EMF of that cell. Imagine though that there is some internal resistance for the cell we have, and most of the real life cells will have some internal resistance, although it will be very, very small. But if you have that internal resistance, if the cell has that internal resistance, then that internal resistance usually is denoted by this way. We show it outside the cell like this, and usually it is shown like this. So now we have the cell terminals. So let me just show what we are doing here. Now again, the blue box is the cell as a whole. We realize that that resistance cannot be really taken out of the cell. It is just shown like that. And this blue box is what you are holding when you hold a cell in your hand. So there is some kind of resistance which is inside that cell, which is now shown like this. Let's say this cell was now connected to some kind of a circuit, and as a result, or you just connected by some wire. So if I connected by some wire, and because the circuit is completed, now there will be a current in this circuit. So this is the positive terminal, that is the negative. As a result, the conventional current flows like this, current I. Now, the terminals are these two. Don't forget, these two terminals are the cell terminals. So I'll call that A and B. And as we know, when I hold the cell in my hand like that, A and B are the terminals of the cell. So I'm interested in finding what is the potential difference there. So if I start writing that VA minus VB, which is also delta V, as we can immediately begin. If it is delta, that delta has to be understood as final minus initial. And see, this is again one of the places where students are a little bit careless, and then they end up having sign mistakes. Delta V is always understood in this manner, in this particular context, as change. So whenever you are actually figure out VA minus VB, you write it as delta V, but that delta is change, which is always final minus initial. And if this is final minus initial, that means your initial location is B. So that means you are going from B to A. And since we are going from B to A, I have to go in that direction. Now when I go in that direction from B to A, don't forget, we will apply Kirchhoff's law and the sign conventions of Kirchhoff's law. So as I go from B to A, now I am going in the direction of current over a resistor. So the potential difference here is nothing but minus IR, because I am going in the direction of current, and then I am going from negative to positive terminal, and therefore that voltage is the plus E, because I am going from negative to positive, and we know this is nothing but the EMF E, as we have already seen. So in this final case, now we realize delta V can also be understood as E minus IR. And that's another equally important relation, delta V equal to E minus IR. If you want to have a consistency check, you can do it. Suppose the cell is ideal, and then of course small r is 0. When small r is 0, then delta V itself is the EMF. That is one good conclusion. But suppose there is no current in the cell. That means the cell draws 0 current. When the cell draws 0 current, I is 0, and once again we get the EMF as the potential difference across the terminals, which is exactly the statement we had made earlier, that when the cell draws 0 current, the potential difference is equal to EMF. And that now concludes our discussion of EMF of a cell.